The three foundation stones beneath the temple at Baalbek weigh approximately 800 tons each. A fourth stone, still partially buried in the quarry a kilometer away, weighs an estimated 1,650 tons. To move that stone with modern equipment, you would need a specialized hydraulic crane system that did not exist before the late 20th century. The site is conventionally dated to the Roman period. Roman lifting technology maxed out at roughly 100 tons under ideal conditions. The math does not work. It has never worked. And recent engineering simulations have made the gap between what Romans could lift and what is actually sitting at Baalbek impossible to ignore any longer. Baalbek sits in the Bekaa Valley of modern Lebanon, roughly 85 kilometers northeast of Beirut, at an elevation of 1,170 meters. The temple complex covers about 5 hectares. The three foundation stones known collectively as the Trilithon are each approximately 20 meters long, 4 meters tall, and 4 meters thick. Their estimated mass runs between 750 and 800 tons apiece. They sit roughly 7 meters above ground level, stacked on a course of slightly smaller stones that themselves average around 350 tons each. The quarry that produced these blocks is located approximately 1 kilometer southwest of the temple platform, downhill from the construction site. 2 unfinished megaliths still rest in that quarry. The first, known as the Stone of the Pregnant Woman, or Hajar al-Hibla, weighs an estimated 1,000 tons. The second, identified in 2014 by a team from the German Archaeological Institute, weighs an estimated 1,650 tons. It is the largest known cut stone on Earth. The conventional dating places the visible Roman temple construction between roughly 60 BC and 250 AD, primarily under the patronage of Augustus and his successors. The Roman temple to Jupiter sits directly on top of the Trilithon course. Whether the foundation stones themselves are Roman is the question this video exists to address. Consider the comparison. The largest stones moved by documented Roman engineering, the Vatican obelisk, transported from Egypt and re-erected by Domenico Fontana in 1586, using techniques recovered from Roman sources, weigh approximately 330 tons. That re-erection required 900 men, 75 horses, and 40 capstans working in coordinated rotation. The Trilithon stones at Baalbek are roughly 2.5 times heavier than that obelisk. The 1,650-ton stone in the quarry is 5 times heavier. By every conventional marker of Roman lifting capability, none of the equipment we associate with multi-hundred-ton stone movement existed in the imperial toolkit. No hydraulic systems, no powered winches, no reinforced steel cabling, no load distribution rigging engineered for masses this size, no surviving textbook describing how any of it could have been done. The largest cut stones on Earth sit at a site where the documented engineering of the era cannot account for them. Serious modern investigation of the Baalbek megaliths begins with Friedrich Rachet, the Austrian architect whose 1980 study, Baalbek remains the foundational technical reference for the site. Rachet was not a fringe theorist. He was a working architect with a structural engineer's eye, and he approached the Trilithon as a transport and lifting problem rather than an art historical one. His conclusion, stated cautiously but unambiguously, was that the methodology required to place those stones was not adequately explained by anything in the Roman engineering record. The investigation has been carried forward in recent decades by the German Archaeological Institute, which has conducted continuous excavation and survey work at Baalbek since 1998 in partnership with the Lebanese Directorate General of Antiquities. The 2014 discovery of the 1,650-ton stone by a team led by Jeanine Abdul-Masih substantially changed the engineering conversation. The stone is partially excavated, still attached to its bedrock matrix, and its dimensions and mass are now precisely measured rather than estimated. The central engineering question is not whether the Romans built the upper temple structures. They clearly did. The inscriptions, the column capitals, the architectural style, and the dating evidence are unambiguous on the visible Roman work. The question is whether the Trilithon foundation course, which the Roman temple sits on top of, was placed by the same builders or inherited from an earlier construction phase. Load path simulations published over the past decade have used finite element modeling to test what Roman polyspastos crane systems could theoretically lift under ideal conditions. The polyspastos was the most powerful lifting device documented in classical sources, described by Vitruvian and Hero of Alexandria. It used compound pulley systems and human or animal power. The simulations consistently produce a maximum lift capacity in the range of 60 to 100 tons, with significant assumptions about ideal geometry, perfect coordination, and unlimited workforce. The Trilithon stones are at minimum 7.5 times heavier than that ceiling. This is the unresolved question the modern investigation is built around. Either the Romans possessed a lifting technology they never documented, never reproduced elsewhere in their empire, and left no archaeological trace of, or the foundation course was already there when they arrived. The fringe theories about Baalbek are louder than at almost any other ancient site. The scale of the stones invites them. The unresolved engineering invites them further. The most prominent alternative explanation is the pre-flood civilization theory advanced by Graham Hancock and others, which holds that Baalbek's foundation course was built by an advanced civilization predating the Younger Dryas climate event around 10,800 BC. In this framework, the Romans simply inherited an existing platform and constructed their temple on top of it without ever quarrying the megaliths themselves. The theory has internal consistency the standard Roman attribution lacks, which is part of why it has gained traction. Erich von Däniken devoted significant attention to Baalbek in Chariots of the Gods, proposing that the platform was an ancient landing pad for extraterrestrial vehicles, with the megalithic stones cut and placed using anti-gravity technology. The reasoning is that no human civilization, ancient or modern, has ever moved stones of this size. Therefore, non-human agency must be involved. The argument is essentially an appeal to incredulity, wearing a science fiction costume. The Anunnaki theory, drawn from Zecharia Sitchin's reinterpretations of Sumerian texts, places Baalbek as a colony outpost of a Mesopotamian astronaut civilization. The textual basis for this theory does not survive contact with actual Sumerologists, but the framework remains popular in alternative history media. A more recent variant proposes that the megaliths were cast in place from a geopolymer concrete formulated by a lost civilization, similar to claims made about the Egyptian pyramids. Petrographic analysis of the Trilithon stones has consistently shown undisturbed natural limestone bedding planes inconsistent with any casting process. The blocks were cut, not poured. What unites these theories is the assumption that pre-modern human engineering could not have moved 800-ton stones. Therefore, something non-human must have. This assumption is doing more work than the evidence supports. The honest position is that the engineering question is genuinely unresolved, and the most likely answer is neither aliens nor Atlantis, but a pre-Roman culture in the Levant, possessing mechanical advantage systems that have not yet been adequately documented. The mystery is real. The supernatural explanations are not the only way to take it seriously. Drone-based photogrammetric surveys conducted between 2019 and 2023 have produced the first sub-millimeter resolution mapping of the joint surfaces between the Trilithon stones. The data has forced a substantial revision of how the foundation course is understood. The joints between the three Trilithon blocks are precision-fitted across contact surfaces measuring over 80 square meters. Gap measurements at the interfaces consistently fall below 2 millimeters across the full length of each joint. This is dimensional precision that, on stones of this mass, modern construction engineers describe as approaching the limits of what is achievable even with computer-controlled equipment. The blocks were not roughly stacked. They were cut to mate. The cut surfaces themselves show tool marks consistent with iron chisels operated under controlled conditions, not the percussive damage that would result from improvised hand cutting at this scale. The marks are uniform across all 3 stones, indicating standardized procedures and trained crews. The bottom surfaces of the Trilithon blocks rest on the course below them, with the same precision tolerances, meaning the lower course was finished to receive the upper course before the upper stones were placed. This is not improvised construction. It is engineered assembly. Petrographic analysis confirms the limestone matches the bedrock at the Hajar al-Hibla quarry, 1 kilometer southwest. The transport route runs uphill, climbing roughly 60 meters in elevation between the quarry and the temple platform. The terrain is uneven. There is no documented Roman road or transport infrastructure capable of bearing 800-ton loads along this route. Modern engineers studying the problem have proposed wooden roller systems, sledges, and graded earth ramps, but no replication experiment has successfully moved a stone of comparable mass over comparable terrain using only documented Roman-era technology. The stone of the pregnant woman in the quarry shows the cutting process arrested mid-extraction. 3 sides have been fully separated from the bedrock. The 4th side is partially detached. Whatever caused the workforce to abandon the stone, it was not lack of technical capability. The stone was being prepared for movement when the work stopped. The physical evidence rules out the casual interpretation that these are simply large Roman blocks. The precision, the scale, and the unresolved transport problem point toward a methodology that has not been adequately reconstructed. In 2019, a team of structural engineers led by researchers associated with the Lebanese University and the German Archaeological Institute published the first comprehensive finite element analysis of the Trilithon course. The study modeled the load distribution across the stones, the stresses on the supporting course beneath them, and the lifting forces required to place them at their current elevation, 7 meters above ground level. The analysis used 3-dimensional scans of the actual blocks rather than estimated dimensions. The model accounted for the precise geometry of each stone, the contact surfaces between them, and the bearing capacity of the underlying bedrock. The engineering question being tested was direct. What lifting technology could place these stones at this elevation, with this precision, on this prepared surface? The results were unambiguous. The minimum sustained lifting force required to elevate an 800-ton block to 7 meters and position it within 2 millimeter tolerance is approximately 7,800 kilonewtons. The maximum theoretical output of a Roman polyspastos system, even when arrayed in parallel banks operated by 1,000 coordinated workers, falls short of this requirement by a factor of roughly 4 to 6 depending on rigging assumptions. The simulation also tested the alternative hypothesis of earth ramp construction, where the stones could be dragged up a graded incline rather than lifted vertically. The analysis showed that a ramp capable of supporting an 800-ton load at the required gradient would itself require an earthwork volume larger than the entire temple platform, with no archaeological trace of any such structure remaining at the site. A separate 2021 study using ground-penetrating radar mapped the foundation depth beneath the Trilithon. The radar data revealed that the foundation extends substantially deeper than the visible Roman construction, with stratigraphic layers below the Trilithon course that predate Roman material culture. The dating of these lower layers is contested, but their existence is now confirmed. The combined engineering and stratigraphic data does not prove the foundation is pre-Roman. What it proves is that the foundation cannot be adequately explained by Roman construction methodology alone. Either the Romans possessed an undocumented lifting technology, or the Trilithon was already in place when they arrived. The math points toward the second answer. The archaeology has not yet caught up with the math. The megalithic construction tradition at Baalbek does not exist in isolation. The Levant and the broader Eastern Mediterranean preserve a pattern of pre-classical stoneworking that consistently exceeds what the standard archaeological timeline predicts. The Temple Mount platform in Jerusalem, expanded under Herod the Great in the 1st century BC, contains foundation stones in the western wall section, weighing up to 570 tons. The largest, known as the Western Stone, measures 13.6 meters long and remains in situ in the lower courses. Herodian engineering capacity is documented in surviving sources, but the methodology for placing stones of this mass is described only in vague terms. The same construction tradition that produced the Western Wall may have been operating at Baalbek at scale. Older still are the megalithic dolmens scattered across the Golan Heights in Jordan, dating to the 3rd millennium BC, with capstones reaching 50 tons. The Rujum el-Hiri stone circle in the Golan, built around 3000 BC, shows organized large stone construction in the region 3,000 years before any Roman presence. Further afield, the Osirian at Abydos in Egypt contains granite blocks weighing roughly 100 tons each, fitted with cyclopean precision similar to the Trilithon joints. The structure is conventionally dated to the 19th dynasty around 1290 BC, but its construction style is anomalous for that period, and some Egyptologists have proposed it represents an earlier construction phase. The same questions that surround Baalbek's foundation surround the Osirian. What this pattern suggests is a regional megalithic tradition operating in the Eastern Mediterranean and Near East that consistently produced stonework at masses the standard engineering history cannot fully account for. The methodology does not appear to have been transmitted in written form. It was workshop knowledge, regionally specialized, applied to specific monumental projects, and ultimately lost. When the Romans arrived in the Bekaa Valley in the 1st century BC, they may not have built the foundation. They may have recognized it. They built their temple complex on top of an inherited platform whose origins they did not record because they did not know. The collapsed distance moment here is uncomfortable. Modern construction firms that move large prefabricated structures, like the segmental erection of bridge sections weighing several hundred tons, use techniques whose conceptual foundations were already understood by whoever placed the Trilithon. We have not invented something new. We have rediscovered fragments of something older. The dolmen builders of the Golan Heights moved 50-ton capstones 5,000 years ago, using nothing but coordinated human labor, wooden levers, and earthwork ramps. The technique is documented through experimental archaeology, conducted at sites in Israel and Jordan during the 1990s. Teams of 200 workers have successfully moved comparable masses over short distances using only Bronze Age equipment. The principle scales. The question at Baalbek is whether it scales 16-fold. Egyptian quarrying and transport capacity in the 3rd millennium BC routinely handled granite obelisks in the 200 to 400-ton range. The unfinished obelisk at Aswan, abandoned mid-extraction around 1500 BC, would have weighed approximately 1,100 tons had it been completed. Egyptian engineers were already preparing to move stones of this mass nearly 1,500 years before the Roman period at Baalbek. The methodology was lost, but the capability is documented in the archaeological record. Roman polyspastos crane systems, when arrayed in coordinated banks, lifted the 330-ton Vatican obelisk into final position in 1586 using techniques recovered from classical sources. Domenico Fontana's lift required 900 men, 75 horses, and 40 capstans. The same equipment scaled to Baalbek's 800-ton stones would require workforce numbers and rigging configurations that approach, but do not quite reach the threshold. The gap is real, but not infinite. Replication experiments specifically targeting the Baalbek transport problem have been proposed but not executed at full scale. A 2003 study by engineering historian J.P. Adam modeled the polyspastos lifting capacity in detail and concluded that arrays of cranes operating in parallel could theoretically reach the 800-ton range under ideal conditions, though the geometric constraints of arranging that many cranes around a single load make the configuration impractical. The paper acknowledges the engineering possibility while questioning the practical execution. The neural hardware available to Roman engineers, to the dolmen builders of the Golan, to the Egyptian quarrymen at Aswan is the same neural hardware available to modern engineers solving comparable problems with hydraulic equipment. The cognitive capacity to design coordinated lifting systems, to calculate load distribution, to plan multi-year construction sequences, was not invented in the modern era. It has been present throughout recorded human history. Whatever placed the Trilithon, it was not magic. It was engineering, executed at the limit of what coordinated human effort can achieve, possibly beyond what any single documented civilization left a record of. The honest position on Baalbek is that the engineering question has not been solved. The foundation stones are real, their mass is measured. The lifting capacity required to place them exceeds the documented limits of Roman technology by a factor that finite element analysis cannot dismiss. The 1,650-ton stone in the quarry sits there as physical evidence that whoever was working at this site was preparing to move masses. No documented civilization has matched before or since. The modern engineering analysis did not reveal a lost super technology or a vanished founder civilization. It revealed a gap. Specifically, a gap between what the standard Roman attribution can explain and what the stones themselves require. That gap is the most important finding to come out of recent work at the site. It is not a gap that fringe theories fill convincingly. It is a gap that mainstream archaeology has not yet filled at all. What still cannot be answered includes the basic question of who placed the Trilithon and when. The stratigraphic data beneath the foundation has been mapped but not fully dated. The transport methodology has been modeled but not replicated. The quarry shows tool marks consistent with Iron Age technology, but Iron Age technology in the Levant predates the Roman presence by centuries and may include cultures whose construction capabilities are not adequately documented in surviving sources. If a megalithic tradition, this sophisticated, existed in the Eastern Mediterranean and left no clear textual record, the obvious question is what else has been lost from the engineering history of the region? Whatever culture produced the Baalbek foundation, the methodology dissolved before it could be transmitted forward. The stones survived. The knowledge did not. The stone of the pregnant woman has been sitting in its quarry for at minimum 2,000 years, 3 sides cut free, the 4th side still attached to the bedrock. The 1,650-ton stone discovered in 2014 has been sitting longer. They were prepared for movement. The movement never happened. Why the work stopped and who stopped it is a question the archaeology has not answered. The largest cut stones on Earth are still waiting in the ground where they were carved.